numerical integration, and this is going to be the last topic of this numerical analysis. So in particular, today we will go through these two schemes. So the rules, trapezoidal rule and the Simpson rule. Just give me a minute. Okay. Okay, so let me just share it again because I'm not able to write it down actually at this moment. So I have to just share it again. So screen. So sorry, so there is something wrong. Okay. Screen. Start presenting. Windows. And this one. Okay, so all right, is it visible now?
Yes, sir.
Oh, okay.
Yes, sir.
Very good. So, do you still see in the full screen or some presenter view or something you are seeing here?
Full screen, sir.
Now. Full screen.
No, it's okay.
It's okay, yeah? We go ahead.
Yes,
okay.
Sir.
So numerical integration, there are two schemes which we will discuss here. One is trapezoidal rule and the another one is Simpson rule. Okay, yeah. So and why do we use numerical integration? The idea is that there are many complicated integrals where you cannot find the value of the integral. So therefore we need some kind of approximation again for those integrals. For instance, if I ask you to compute 0 to 1 e power minus x squared dx, then you cannot compute this exactly. You don't know what is the exact value. Yes?
Yes.
Any question?
Any question?
No?
No.
Okay.
Okay.
So table actually there is some issue. Yes. What's your question? So the second integral, which also you see here, that x power pi sine square root x. So this is also a similar kind of a situation where you cannot actually find the exact value of this integral. So there are many schemes. Some of them we will go through. In general, they are called Newton-Scott's integral formulas. So one of them, wait. So something happened. So one of them is trapezoidal rule, which we will now learn. So in this, in general, in the Newton-Scott's integration formula, these formulas are based on replacing complicated functions. So basically, your integrand or sometimes you have tabulated data also where you need to integrate that function which fits through this goes through that given data. So in any case, the idea is that we will replace that complicated function or tabulated data by approximating function that is easy to integrate. And in particular, we are talking about the polynomials actually, because polynomials are easy to integrate, as you know. So this function here, which is usually complicated like given in these two integral, we will approximate by some polynomial of certain degree. And based on different degrees, we have different names, but in general, these are called Newton's Cotes integration formula. So the trapezoidal rule, and I have written here single application. What does that mean? I will come to that point. So just wait. So suppose your integral is a to b fx dx. So wherever you have query, you please let me know. But it is a very simple topic, and hopefully we'll finish it today itself. So we have integral a to b fx dx, and in this trapezoidal rule, the idea is that this fx we will replace with the polynomial of degree 1. That means the straight line. And what is that straight line and the connection to this fx, that I will explain you in a minute here. For instance, your function is this fx that given by this red line. That is your actual function. But what we are doing in this approximation, we are considering only 2 points, the value of this function at this a point, the value of the function at this b point. And considering these 2 points, so the first point here is AFA and the second point is here BFB. So considering these 2 points, we will fit a line. We will approximate that function by a line. Naturally, you see it's a very bad approximation. So we'll come how to improve that approximation. So we will fit by the straight line passing through these 2 points. And then this polynomial, the straight line, we have already discussed in earlier chapter where we have the idea of interpolation. So this P1x which passes through these 2 points will be given by FA, FB minus FA over B minus A, that is the slope, and this x minus a, that is the straight line which we have already discussed in the previous chapter, previous lecture. So here we have replaced this function by this polynomial of degree 1 which is given by this expression, and now you can integrate this. And after integration, because it's a simple integral, so I can go through, for instance, here fa is constant, so fa into this b minus a, that is the value of the integral. In the second case, you have x minus a whole square by 2, then upper limit minus lower limit will give you this half b minus a whole square. And when you simplify this, you will get actually this one, b minus a fa plus fb by 2. So what is our formula if we want to approximate this integral from a to b of this fx? So this fx will be replaced by this line here and the value of this. So basically you are looking for this area of this trapezoid, yeah? So which is fa plus fb by 2 and then b minus a. So that is the actually the area of this trapezoid here, which I have this marked with these red lines. So is that clear now up to this point, or any question do you have here?
Yes, sir.
No question, right?
Yes, sir.
Okay, well, so this is why I have written a single application, that I have applied in this range a to b only once. That means I have taken only these 2 points, the end points, and then approximated by this straight line, and then the area of this trapezoid I'm calling as an approximation of the actual integral, and this approximation is given by this fa plus fb by 2 into b minus a. For instance, we have this example here, the trapezoidal rule. You integrate numerically such a function and compare your exact value with the value of this integral, exact value of this integral, which is 1.640433. So suppose we do so now. So f0 And we want to integrate from
What
yeah,
what are the limits of the integral?
yeah, that's what I forgot there. So it should be 0 to and 0.8, I guess, from this itself here. So 0 to 0.8. So if you integrate this 0 to 0.8 fx dx by this rule, so you have fa plus fb by 2, you evaluate this f at 0. So 0 means you have just 0.2 there, and you need to evaluate at 0.8. So you just substitute here 0.8, here also 0.8, then 0.8 is square, 0.8 cube, and so on. So that you evaluate, it will be 0.323. So we are not spending time here on these evaluations. Divided by 2, and this 0.8 minus 0, and the value is 0.1728. The value is 0.1728. Naturally, you can see that this approximation is a very bad approximation, because the actual value of this integral is 1.64030433. So this is a very bad approximation. The reason is clear, which was obvious from the previous figure also, because you don't know how your function is going between these 2 points, but you are just approximating by a straight line. So naturally, you cannot expect a very good result if your function, does not behave like a straight line in between these 2 points. Well, now that's the reason we now get to this multiple application of trapezoidal rule. So instead of having just 2 points from A to B, the idea is that we can break this interval into several points, right? Into several intervals, so sub intervals, and then we can apply this trapezoidal rule in each interval, right? I mean, why to apply once? We will apply in several intervals. So that means this x naught is a, we are denoting by x now. So then we have x1, x2, x3, and so on up to xn. So how many intervals we have? Because x0 to xn, we have divided the whole range. So there are n intervals, right? So there is always one more point. So we have n plus 1 points, meaning we have n intervals. So we have divided the whole range into n interval, and then that part will be taken care, because instead of applying just once that trapezoidal rule, if we apply in the smaller part, then naturally that error will be less, because in each interval now the interval size is very small. So the error is going to be also small, because then your linear approximation is not a very bad approximation when your interval size is very small. Well, so we have considered n plus 1 equally spaced points, that means n interval. So this b minus a range of the whole interval, when we divide by n, we got that h, the size of the interval. That means your integral now I, we have divided into several parts. So x0 to x1, x1 to x2, xn minus 1 to xn, and so on. And in each interval now we will apply the trapezoidal rule. So in each interval means, now the first integral, if you consider here, you have fx0 fx1 divided by 2 multiply by h. Then again in the second case, fx1 plus fx2 divided by 2 into h, and so on. You continue with this, and the last integral will be xn minus 1 and fxn divided by 2 into this h. Now we can sum it up, and then you consider also that there is a fx1 here, also fx1, then fx2, you will have fx2 there, and so on. So these, except the first and the last one, you will have these repeated one. So then when you take this h by 2 common, then what you have the first point fx0, and the all internal points will be just having 2 as their product. So 2 into fx1, fx plus fx2, plus fx3 plus fxn minus 1, and the last point. So what is our formula? Our formula is h by 2, then you have fx0, 2 times all the sum of the function at internal point, and then you have the last point fxn. Is that clear now, this formula?
Yes, sir.
Yeah, so when you have trapezoidal rule, you break into several intervals, small intervals, the value at first and last will be just summed, and all internal points will be doubled. So the 2 times the function value here, you have the sum of all these internal points. We get back to the same example. So we want to integrate from 0 to 0.8, and we have just divided into 2 portion. So 0 to this 0.4, and then 0.4 to 0.8. So our h is just 0.4, and then you have the function values at all these 3 points, and then you apply the trapezoidal rule. That means h by 2, the function value at the beginning, the function value at the end here, and then 2 times the function value in the middle point, so 2.456. And when you simplify this, you will get 1.0688. So still we are far away from the actual value, but much better than the earlier one. If you remember, when you have taken just one interval, the value was something in not even one, was some point something. Well, fine. Shall we go ahead, or do you have any question?
Yes, sir.
Sir, how to which value of n we should take?
Loud, please. So your voice is very on off. Yeah, so I could not hear.
Sir, how should we decide which value of n we should take?
See, the more n you take, the better result you will get. It's a simple algorithm. So you have more points, your approximation will be better. If you have something preset that my approximation should be better than this value, then we will use, which I am going to also teach you, that error. So that error will help you, that how much error do we have, and then we'll have some one example at least of that kind. Yeah, so I'll answer your question. So for
Excuse
that,
me, sir.
yeah, please.
Sir, I was just asking that why we are naming this as a new method, because isn't it the basic only of integration, that how we are derived integration in class 12?
Yes, sir. The integration is same, but it's not the integral of fx. Yeah, we are not integrating fx. We are approximating that fx, right? So you have a to b, sorry, a to b fx dx. So it's the same integral, but why we are calling numerical integral? Because we are not computing integral fx to dx, but rather we are approximating it. So how to approximate, how those formulas are coming? It's based on that approximation. So this fx we have at first here in the trapezoidal rule, we have approximated that fx by the polynomial of degree 1. And then we got that formula that it's nothing but b minus a multiplied by f function value at a plus function value at b by 2. That is actually the formula of the trapezoidal rule. So obviously integral is same, but why we are calling numerical? Because this you may not integrate exactly. This fx may be very complicated, as I have just written 2 examples at the very beginning, and therefore you need this idea of the numerical integration. Is that clear? What is the difference?
Yes, sir. Sir, and I think also we had done the same thing in Riemann series when we were doing studying that.
Yes, actually, yes, you are right. But the difference was that there we have learned that that limiting case will give you exact solution, right?
Yes, sir. Yes, sir.
Limiting of this, that you break into small sections, and then of each this trapezoid you get the area, and once you say that n goes to infinity, then that is going to be actually, yeah, exactly, that is the basic starting point of that integral. True. But now we are calling that, okay, we will restrict to some finite number, right? We are not considering that limiting case, because in many cases that limit you may not evaluate, not possible. So we are just approximating that by taking some finitely many integral. And this is not all. Yeah, so this is just a trapezoidal, one kind of rule, which you will find it is not a very good approach of approximating integrals. So we will have something else next, which is so-called Simpson's 1/3 rule. Yeah. So we'll discuss a bit on error analysis. So here we'll go through quickly, because if I spend too much time, then our lecture will be just on this error part. So though most of the teachers are just referring that this is the error, so I will just go through quickly, and I'm sure that if you have these slides and all, you can understand yourself. For that, I need to explain you maybe a new result, which is called weighted mean value theorem. Weighted mean value theorem, and that is for integral. Yeah, integral, not for differential calculus. It's for integral calculus. Here, what do we have? We have just go through the statement here that f and g are continuous in this AB, in this interval AB, and there is another condition that G never changes sign. So if it is positive, it will remain positive. If it is negative, it will remain negative. Then what result we have, and I will not go through all formal proof of this result, that integral a to b fx dx, you have the product here in the as an integrand of these two continuous functions, and one of them does not change sign in this whole interval. In that case, you can write down this integral as, or this will be equal to, yeah, there is no approximation or anything we are talking about at this moment. It's an analytical result. You have equal to here f at some point c. Again, this is coming from Lagrange mean value theorem. When you go through the proof and all, we have the Lagrange mean value theorem, nothing else. So you have the f evaluated at c. So there exists some c in this whole interval AB, where this integral will be equal to fc and the integral of the rest ab fx dx. So this is the weighted mean value theorem for integral calculus. So you have a to b, again fx dx. I will go to the special case of this. For instance, I just say g is 1. Yeah, if g is 1. So what do I have here? A to b fx dx will be equal to f at some c, and integral a to b will be just b minus a. Yeah, or I can write down here 1 over b minus a, that range of this integral a to b fx dx is equal to f at c. It's some kind of average. Yeah, so you are integrating here a to b fx dx, you are integrating, and then you are dividing also with that range a to b, and that is equal to the function value at some point c. So this is a kind of the average of this fc here, which, because since the function is continuous, so that average value will be somewhere within that function given function range, so fc. So yeah, I'll not tell you more about this now at this moment. So just remember, this is a more general result, that a to b fx dx is equal to fc and integral a to b gx dx. This is the result. The second counterpart of this, which is called discrete mean value theorem, which is quite similar to this one, the weighted mean value theorem for the continuous function. Here we have one function which is continuous again in AB, and let xj be n plus 1 points again in this interval, and cj's be n plus 1 some constants having same sign. Again, the cj's are either plus or minus. And then again, similar kind of idea that there exists a xi or c, whatever, in AB, such that the summation of this cj fxj, similar to the earlier one, there we have the integral, because we were talking about everything continuous. Now we are taking about the discrete points. So the sum cj fxj will be equal to, again there it was fc, here we have this f xi belongs to again somewhere in AB, and the rest is sum, as there it was integral. So this is also so called the discrete mean value theorem. And again, in particular, if you see that your cj is 1, then you are getting that 1 over n plus 1 j 0 to 1. This is a mean again, right? When you have this n plus 1 points, you are summing all those and dividing by n plus 1, and we are saying that this is equal to some f at some xi. So these are the two results. You can remember one, the other one is of course clear, but that is needed for the error analysis part, nothing else. So if you find it difficult anything, you can also leave it. So we are not going much into the detail of the error itself. So, and hence these two theorem as well. Good. So the error bounds, we want to calculate how much error we are doing when we are approximating our integral by trapezoidal rule. So let's calculate with this in single application when we are applying just once that trapezoidal rule. So remember that the difference between the function and the polynomial, right? This was discussed in polynomial interpolation. And if you remember or get back to the earlier lecture, the difference, the error between that polynomial and the function was given by such expression x minus x naught, x minus fx, x minus x1, the second derivative at some t point divided by 2, and this t is somewhere this between x naught and x. Yeah. So now we integrate here both the sides, we integrate. So this was the error, yeah, error in interpolation. You can just get back and look it again. This t here again I have written that depends on x and lies between this x naught and x1, the 2 points you have considered. So this t is somewhere in that interval. Well, so if we integrate that, we will get this fx integral from that point x naught to x1 point, and minus this p1. When you integrate, you will get that formula of the trapezoidal, the area of the trapezoidal, and equal to here also we integrate that. So this is actually the error we are trying to compute, because this is the difference between the integral. This is the integral, actual integral, and this is with the trapezoidal rule. Yeah, this is with the trapezoidal rule. So this difference, the difference between the two, we are calling error, and we want to see how much error we have if we approximate our integral by trapezoidal rule. So that error can be estimated by this integral now, which and this integral we got this error formula from that interpolation section. And here, once we integrate this, we will see what is exactly coming. So this x minus x naught and x minus x1, just see that it does not change sign. It does not change sign whatever x you have in the whole range, x naught to x naught plus h, because this one is going to be positive, this one is going to be always negative. So you have the negative sign, and it will remain negative. So it will not change sign. So this is our function like g we have discussed earlier. This is something like g. The second, here you have the function f prime t, as we assume continuity and all of this f prime t also. We can now apply that mean value theorem. So applying that mean value theorem, we can take this f prime t, f double prime t outside the integral at some point t prime, t tilde, and then the rest is the integral, which we have just learned on previous slide. And this integral you can actually evaluate, because it's a very simple one. You have just a quadratic polynomial here. You can integrate it directly or by substituting, whatever way you integrate this. So I am substituting here x minus x is equal to, or x minus x naught to v, x minus x naught to v, and then dx. So just to simplify this, nothing else. So, or directly you integrate. So whatever way you do, what you will get this here, minus h cube by 12, and the double derivative evaluated at t tilde. So t tilde is somewhere again between x naught and x1. So this is the error, because this was exactly the error we have started with e. Yeah, e is here. So this is the error here. What we got, h cube by 12 and f double prime. So double derivative at some point in this, we don't know exactly at what, but important is h cube by 12 is this factor here. So now I'm moving. So this was a single application. Yeah, when we apply in a single integral or a single integral, then we get error as h cube by 12 f double derivative. Now, since in most of the cases or every time we'll be applying for multiple intervals, not just for single interval. So let's do that. So once you apply for several intervals, in each interval you are you will be having this error h cube by 12 and f double prime t. So we sum up all. So we are summing up here all these errors in n intervals from 0 to n minus 1. So we are basically summing up for n intervals. H cube by 12, that is a constant term, and you have here the summation f double prime. And then using discrete mean value theorem, if you remember that is special case we have learned there, that will be nothing but n into f double prime again at some point t, which is again in this between your range, from x naught to xn. Well, and this is what we have written now here. 1n with this h, n into h, that is nothing but b minus a, because this is exactly we have started with that your if you divide into n interval, then your h will be nothing but b minus a over n. So from there we got one this n and h because they are related. So you got this b minus a divided by 12 and then h square and the double derivative. So the h square term is important actually because your error, the rest is somehow constant. So b minus a divided by exactly constant and the double derivative, which you may find the maximum value in that range. So what is important? Important is h square. So as you are making that edge smaller to get a better accuracy, your error will reduce by square. So it's a quadratic kind of convergence which you see here in this trapezoidal rule, and which is not bad actually. You are that with this just a simple consideration that replacing that by straight line, that curve within the given interval, your error is getting by reduced by h square, where h is that step size. So this is the error. If you want to take the bound of the error, because see this t hat is not known exactly where it is. So the remedy always is that you can get at least the maximum value. So the maximum of x naught xn, you look for that maximum value, and then you have this error bound e will be bounded by b minus a h square and divided by 12 into this m2. M2 is the maximum of this double derivative in that range. So this is the error bound. That error will be always bounded by this one. So your h is small, you will have a small bound. So your error will be small basically. So it is directly related to h. Yeah, in fact, in terms of h square. So if you quadratically reducing your error or going towards zero. Is that okay? Some quick, yeah. So we got some idea at least that how this error is related to the number of intervals or h, the step size. Fine. Do you have any quick question here? Or individually you can ask if you are interested. Just go through and let me know if you did not get the idea. So you can write to me. I'll try to explain you. Well, now we evaluate the following integral using trapezoidal rule, taking n 2 and 4. So calculate numerical value with the exact solution. Okay, we'll compare. It's basically compare, not calculate. Compare with the exact solution and find the bound on the error. Well, also find the number of subintervals required if the error is to be less than 5 into 10 raised to the power 4. So your answer to your question, well, you said that how many points we should take. So obviously first we have to define the tolerance, that how much accuracy we expect in our numerical calculation, in our numerical approximation. So based on that, you can actually compute the number of subintervals required if you want your error to be less than a certain value. So here we will see few things now. First, with the trapezoidal rule n2 and 4, we will compute the value of this integral. We will compare with the exact solution, because exact solution you can get in this problem. We will find the error bound. Yeah, and we can compare actual error with that error bound also, that it is really less than that error bound. And then we will also compute that if we want to have our error less than this, then how many sub-intervals we need to take. Well, so the case 1 is the number of sub-interval 2 if we take. So h is 0.5. So because 0 to 1 you are just going with 0 to 1. So this is first interval, then this is second interval. So of course your h is just 0.5. So h is 0.5. You apply the formula. So h by 2, you have f0 plus f1 and 2 times the middle value, which is f 0.5. And once you compute this, you will get 0.2583. We will compare a little later what is the actual value. We will also see. Number of subinterval 4, if you want to take, then you will have, of course, 0.25. So once you have want to take the 4 interval, so you have this interval width 0.25, and which makes here from 0 to 1. So h is 0.25, and then again you apply that formula. So half of this h, then f0, f1, and then 2 times the values at 1 by 4, 1 by 2, 3 by 4, because your points are 0 and 1, and here you have 1 by 2, here you have 1 by 4, and here you have 3 by 4. So you compute these 3 internal points, make this double, and then first and the last point, that's your approximate value. So when you compute this, you will get 0.2561. So these are the computation for taking interval 2 and 4. Now we will look for the exact solution. The exact solution will be coming 0.25541, and these are our values. We're using interval 2 was 0.25833, using interval more, so 4 intervals 0.25615. And the error in each case you can compute. So in the first case your error is 0.0029, in the second case it's a 0.00074. This is the actual error. The difference between the numerical value and the actual value. Now we want to get the error bound. So remember that formula was b minus a h square by 12 m2, where m2 was the maximum value of the double derivative. So we can compute double derivative of the integrand, which is 8 over 3 plus 2x cube, and then here you have m2 is equal to 8 over 3 plus 2x cube, maximum over 0 to 1, and the maximum will be achieved, of course, when x is 0. So you will get 8 by 27. That is the maximum value of the double derivative in that interval 0 to 1. Well, we have this bound, so we can get the error bound with this error formula here, which is b minus ah square by 12 into m2. Keep m2 as 8 by 27. So finally our error is 2h square by 81. 2h square by 81. That is the upper bound of the error. Error cannot go beyond this. Whatever your h is, you put it here, you will get the value. So for instance, when your h was 0.5, your h was 0.5, you error you can compute from here, it will be coming 0.0067. And what was the actual error? The actual error was this one. The actual error was 0.00292, which is of course bounded by this upper bound. And when you take h is equal to 0.25, you compute again in this case here 2h square by 81. This is coming 0.00154, and naturally the actual error here is less than the upper bound. So actual error was 0.0074. So in either case, yeah.
So in some functions we won't be getting the actual error, so then we have to rely on this bounds of errors only.
Yeah, so if you don't, because obviously you will not get the actual error, because for those functions you don't have the actual value of the integral. So this error bound may help you to give some idea that how much error do you have the upper bound, until unless you get these, because here also you need to get the double derivative, and then double derivative you have to get the upper bound of the double derivative. Once you have this, you can get, yes, the upper bound of the error. Yeah, so you will get some idea of the error with this error bound. That is true.
Okay.
So now the third question was that you want to keep your error less than 5 into 10 raised to the power 4, right? So we will do exactly this one. So this is our error bound. This we want to keep less than 5 10 raised to the power minus 4. So the maximum, bound we have there, b minus h square by 12 m2. We want to keep this even smaller than 5. So then we are sure that once this is satisfied, we are sure that our error will be less than 5 into 10 raised to the power minus 4. And now this m2 we had already computed, 8 by 27. Keep it there. Then this 5 into this, I convert this h in terms of this n, because there is a relation b minus a divided by n is equal to h, so that h can be converted into n. So we have this relation. Out of this relation you get this n. So once you do that calculation, you will realize that your n should be greater than 7.03, and n is the integer. So if you take 8, if you take n 8, you are safe, and definitely your error is going to be less than this one if you take n 8. So the required, it may happen that 7 itself is enough, because we are doing this calculation with the upper bound of the error. So it may happen that 7 also gives you error less than this, but you are not sure, right? In your calculation, through your calculation, you are not sure that what will happen if you take 7. But 8, you are sure that if you take 8, definitely your error will be less than 5 into 10 raised to the minus 4. Good. So we got the overall idea of this trapezoidal rule. True.
Yes, sir.
Yes, sir.
So it's a very simple one. Nothing. You just go through once again, do few more examples over. This is, I think, the easiest part so far. Similarly, with the Simpsons one-third rule also, and we will teach only these two, Simpsons and trapezoidal. Simpsons, just an extension. The instead of taking P1, you take P2. You take polynomial of degree 2. And for the polynomial of degree 2, how many points do you need? You need 3 points, right? You need 3 points. You need 3 points to fit a polynomial of degree 2. Earlier case, we were using only 2 points, but now we will use 3 points, because we want to fit by a polynomial of degree 2. Clear? Okay.
Yes, sir.
So we will take x0, we will take in the middle x1, and we will take x2. We will take 3 points now, not 2 points. The boundary point x, a and b, and somewhere in the middle x1. So once you do that, remember, yeah, I have just written here, this Lagrange,
Lagrange's,
yeah, from Lagrange interpolation, that polynomial. You can, whatever, that is polynomial is clear. That's a unique polynomial which passes through these 3 points. So with this, simple calculations, do yourself. I will not explain you. It's an integral only, because you have the quadratic term in each. So you just simplify and integrate it. And after integration, the important thing is here that after integration, you will get h by 3, f at x0, f at x2 means the end points, right? fx0 and fx2 are the end points. And 4 times the middle one. 4 times the middle one. This is the formula. H by 3, 1/3. Yeah, from 1/3 you can remember this h by 3. So 1/3, and then fx. There are other Simpsons also, not only this 1/3. There are other 3, 8, and so on. We are not going to all those methods. So 1/3, fx0, fx2, and the 4 times the middle one. Well, this was for single application, right? When you are applying this Simpsons 1/3 rule once, yeah. Well, multiple application, that means again you will break into many, but remember, you have to have 3 points, then 6 points or 9 points, then only you can apply. So you should have either 2 intervals or then 4 intervals and so on. Yeah, 2, 4, 6, those intervals, then you can apply. Otherwise, you will not end up with exactly covering everything. So here you have x0 to x2, then x2 to x4, xn minus 1 to n. So every interval has this range x0 to x2 has one more point. That means two intervals. Yeah, you need two intervals to apply a Simpson rule. So you have two interval in between, here also two interval, there also two intervals. You apply that fx naught 4 fx1 fx2, here fx2 fx4, then 4 fx3, again fx n minus 1 fxn, and then again 4 times the middle one fxn minus 1. And then simplify again, because you will see that fx2 and here also you have fx2, fx4 and you will have fx4. So those boundaries will merge. So you have x by 3 common, then you have fx0 4 times. Just remember 4 times the odd one, means 1 3 5, those 1, then here 3, and so on. Those will be added with 4 times. 2 times which will be added with x2, x4, and so on. So with 2 times you have 2, 4, 6, and so on you add, and the first and last naturally just the addition without any weight. So fx naught and fxn, these are there. Earlier also it was there, but now you have two cases here, 4 times the odd ones and the 2 times the even one. You can remember. Error, I will not derive the error here, but in this case you will realize that in single application the error will be h5 over 90 f4, and when you have the multiple application like here we have seen, you have actually this is the error bound in case of the Simpson's 1/3 rule, b minus a over 180 h4 f4 and so on. So here you can see that Simpson rule is much better, because here the error is of order 4, of order h4. Earlier it was of order h2. So that is the difference. We want to evaluate this dx over 3 plus 2x, the same case, compare with the exact solution. Take n is equal to 2 and 4, the same like earlier. So n2 means this one. We will have just a single application of Simpson rule. So you have f0 1 by 3, then 4 times the f half, and then the f1. So once you do that, 0.2556 will be the value. For n is equal to 4, you again apply here the 4 times this one and this point. Yeah, this will be the with the 4 times, and the 2 times, sorry, here the 2 times will be this half. So see which one alternate. Yeah, so you start with this one which is 4 times, then this will also be 4 times, and then these will be 2 times. Well, so it's a 0.25542, and exact value was 0.2554. So you see it's almost matching now with your exact solution, exact value of the integral. Good. So the numerical integration, we are almost done now here. We have the only two rules, the trapezoidal one, which this formula you need to remember, h by 2 fx naught, the 2 times the sum at these internal points, and then fxn. And the error was of order h2, which we have to also remember. The Simpson's 1/3 rule was given by h by 3 fx naught fxn, and here 4 times, here 2 times, and then you add, you will get the value. Here the error was of h4, and fourth derivative, of course, h2 the second derivative, h4 the fourth derivative, and the front here it was xn minus x naught by 12. Here it is xn minus x naught by 180. That is what we have learned today. So if you have any question, we have at least 5 minutes for discussion. Yeah, so we are done. It was too fast, I guess, but only 2 terminologies we have learned, and that too they are very basic, the trapezoidal and the Simpson 1/3 rule. Yeah, so any question do you have?
Sir, I have one doubt in
Tomorrow
the
we will
trapezoidal
start
rule.
the complex. Sorry?
Sir, I had one doubt in the trapezoidal rule.
Yeah, go ahead.
Sir, if we instead of reporting the value of the approximated integral, if we report the value of integral plus the error, then will it be closer to the actual integral?
Yeah, but where? Because there also you have this double derivative which is at a known point. So it may happen that again you will take some approximation to this double derivative, right? So that double derivative you will take some upper bound for the double derivative. When you add that error there, I mean there is no guarantee that whether it will be better or it will be worse, because there also the error is not known exactly to you, isn't it? That is coming in terms of the double derivative. Yes, and which is at a known point. So that double
So what if we
derivative.
use the bound, like the max bound for the error?
Sorry.
So what if we use the max bound for the error, that term, that error,
Yeah,
if we are?
that I also explained before, just in this example, that how we can use it. So at least like where was that example? Yeah, this one. So for instance, we wish to have our error in this trapezoidal rule or Simpson rule, whatever the same exercise you can do there, that we want to make sure that the error should be less than 5 into 10 raised to the 4, or any number 10 raised to the minus 6 you set, or anything, that my error should be less than this. So how many points should I take, if that is the question? So you can estimate this. So once you have this error estimate, this is your error estimate. Your error estimate is this one for this particular example. This is your error, correct? This is the absolute value of the error. So if this error, which is the upper bound, yeah, the error in your actual calculation cannot go beyond this, and then you are setting this itself to less than the given tolerance, and then compute your n, then if you take this n, this will guarantee, this n is equal to 8 will guarantee that the error is less than 5 into 10 raised to the minus 4. So though in practice, in practical problems, I don't see much application of this error, honestly speaking, because whenever a problem is given, I'm not going to compute first this error or anything, error bound or so, because that integrand is too complicated. First of all, yeah, that integrand is too complicated that I'm not able to exactly get the value of this. And with that complicated integrand, will I look for the second derivative? Actually not. So I will just, there are many other ways also to see the accuracy. You take 100 points, compute it, then take maybe 120 points, again you compute. So for example, here the value of your integral is 1.2359, and now here you compute 1.3219, then you will see, okay, at least some changes are there, but then you will go maybe 130, then you will say, okay, 1.3225, oh, there is no change in 2 digit. Okay, I think that's fine. So I will go with this 130 points. So that way you can see that how far or how much decimals are meeting when you are increasing the number of points, but never with this error formula. So these error formulas and all are very much used in analysis. So once you do analysis where integrals are involved and there are many other things are involved, so there in analytical calculations you can replace that error by this error bound. So you know that, and then you prove this. For example, here we have observed that the convergence of this towards the actual value. So this trapezoidal rule, you have the error h square. Yeah, error is proportional to h square, whereas this one is for h4. So you know that which one will give you really better results. Of course, Simpson 1/3 rule, because here the error is h4. So all those benefits are there to analyze, because without this analysis, you don't know how much the Simpson, you may expect that Simpson will give h3. according to the basic calculations, there was a polynomial of degree 1. Here you have polynomial of degree 2, and the expected result was h3 actually. But there was some cancellation happened, and then we got actually luckily this h4. So, but which we came to know while doing this analysis. So those results are useful, but not maybe very practical, that once you want to get this approximation value of the integral, first you will evaluate these results and all. Of course not. Fine. So in that way, this is important.
Excuse me, sir.